let me just introduce the new speaker then. Anna Florio, we've been wanting to have her talk at one of our events. By we, I mean the people, the old people who have run many of the events of the DinAmica lately, and we finally got it. So I would like to thank Anna for accepting our invitation. Anna is now at Sorbonne University. She's a postdoc of Fondation des Sciences Mathématiques de Paris. So I don't know if it's a place or rather than an attribute of her postdoc. Maybe she can explain it to us. Coming from a PhD in mathematics from Avignon under the direction of Marie-Claude Arnaud and Andrea Venturelli. And before that, she was at Université di Padova. She studied with our own Olga Bernardi. She's been very busy lately on, if I understand correctly, if I'm wrong, Anna, on chain recurrence, and she branched out to other interesting topics as well, such as, for instance, spectral rigidity of systems. And in fact, her talk today will be about, and that's the title of her talk, spectral rigidity of contact 3D Axiom A flows. So once again, thank you, Anna, for joining us today, and here's to you.
So thank you. So good morning, everybody. I really thank you, the organizer, for this kind invitation, and I'm very happy to be here. Let's see, virtually, and so let me just share my screen. So could you see my screen?
It's all nice and clear.
Okay, perfect. So today I would like to speak about spectral rigidity for contact 3D Axiom A flows. So this is a joint work with Martin Leguil from Université de Picardie. So let's start about what I mean by rigidity questions. So the main aim of our work was that I tried to give an answer for some particular system to the following question. Imagine that you have two smooth dynamical systems, and you know that they are topologically conjugate, and you want to know if there are some conditions that could assure us that the two systems are actually conjugated, but in a smooth way. And just to give you a little bit state of the art and some overview of what could be found in this kind of in this framework, this kind of question already arises in very lower dimensional dynamics. So in particular, think about circle diffeomorphism. And I would like to say that like the main motivation could be searched in the famous Dungeon theorem, who says that as soon as you have a diffeomorphism of the circle that is regular enough, so think about C2, for example, with some irrational rotation number, then the theorem shows us that it is topologically conjugated to a rotation of the circle with the same rotation number. And in this framework, so first result about, in particular, analytic linearization were obtained in the 60s by Arnaud, who proved that as soon as you work with an analytic diffeomorphism of the circle that has a Diophantine rotation number, so an irrational rotation number that is badly approximated by rationals, and which is, let's say, sufficiently close with respect to some norm to the corresponding rotation on the circle, then it is actually analytically conjugate to the rotation itself. So it's you gain, of course, much more regularity. And also in this direction, I wanted to mention further works by Hermann at the end of the 70s, who generalized actually this result in smooth and also differentiable framework, and he proves also some optimality result for the Diophantine condition in the smooth case. And later on also by Jean-Christophe Yocos, who in the analytic case shows that the optimality for this kind of rigidity result is obtained when you have a rotation number that satisfies some Bruno condition. And all this kind of rigidity results for circle diffeomorphism are based on some tools that comes from renormalization techniques. But what can be done when we go to let's say upper dimensional dynamics? So in particular, already in concerning surface diffeomorphism, actually. These techniques are not so easy to generalize, and there are some other tools that must be developed and used to try to answer this kind of question. So in particular, thinking about surface diffeomorphism or three-dimensional flows that are hyperbolic. I will come back later to the precise definition. There are some natural obstructions that arise that are in particular linked to the periodic orbit. Indeed, each periodic orbit carries with itself a possible obstruction to the let's say regularization of the conjugation, because in some sense you have to match the Lyapunov exponents so coming from the Jacobian. And but as I said, there are some other tools that could be developed, and in particular there is that will be also the one of the tools that I will we use also in our work. We could try to use the hyperbolicity to work actually with the invariant foliation, so in particular stable and unstable foliation, study then the regularity of our conjugation along the leaves, and then use some journey type arguments to gain actually the regularity on every direction. And in particular, so in this framework, some results have been obtained. So already for Anosov systems, and also for hyperbolic sets of still surface diffeomorphisms in terms of the Lyapunov exponents. Indeed, there are so different authors. I'm sure that maybe I'm forgetting somebody. And in particular, the different works, it is proved that where there is this hyperbolicity that arise, the Lyapunov exponents actually gives you a complete set of invariants of the smooth conjugacy classes. But so what I mean that the two systems that you are looking at are smoothly conjugated if and only if they are topologically conjugated, and they have the same Lyapunov exponents. So, this kind of question also could be related and could find some application also for concerning some systems arising from geometry. And so, just to give you some example. Think about the geodesic flow on surfaces with negative curvature, where there are lots of works about. So it's a different kind of rigidity, but I could say it's not completely independent. With the works, for example, of Guillemine Katzdam in the 80s, and then Otal and Koch in the 90s, were and more recently in any dimension, recent paper by Guillermo Lefebvre, where actually the flows are more concerned about given a compact surface with a negative curvature. Let's fix a two Riemannian metric and just compare the geodesic flow And the question is like under which condition. So if you have some if the two geometric flow share some what is called the marked length spectral, then you know that the two metrics that you are looking at actually are obtained one from the other through diffeomorphisms. And moreover, another field, another framework of interesting, dynamical systems when we could look at this kind of question are planar billiards. So in particular, for example, convex billiards, and moreover the case of dispersing billiards, but I will come back later. I would like to spend some few words about it later on. So let me start first of all to define and to explain a little bit what are the systems in which we are interested in. So we want to look at contact three-dimensional axiom A flows. So let's just spend some words about what I mean by contact. So I will do some reminders, I think, for most of you. Contact dynamics are, I found it extremely interesting dynamics that arise from some contact structures in the following way. So let's think about a three-dimensional manifold oriented. So oriented. And let us consider a contact form alpha on this manifold. So a contact form is just one form such that when you consider alpha wedge d alpha, this gives you a volume form on your manifold. And so in particular, it allows you to determine an orientation that you can use to equip actually your manifold with it. And once you have your contact form, you can look actually at the kernel of this contact form. That is a plane field, and it is called actually a contact structure. So let's just give an example of let's say the more standard contact structure. Just take as a manifold so R3 and consider our contact form alpha, so minus y dx plus dz. The fact is that you can once you have this contact form at any point, you can think about looking at the tangent space of the point and decompose it. Like at any point, you will find a plane that is evolving continuously with respect to the point. And so let's think about some plane like in the picture that are rotating. And actually it is so the most simple example, but it is also the standard one, because in the contact framework there is also in the contact framework, as in the symplectic world, there is a Darboux theorem that assures you that as soon as you have a contact manifold is so let's a 3D manifold and with a contact structure, you can describe it locally exactly with this model. And once you have your contact manifold, you can then consider the rep dynamics that is so determined, let's say, by your contact form alpha. Indeed, to given alpha, you can associate it to it a rep vector field x that is defined by the following condition. So you ask that d alpha x is equal to 0. So just So you just that d alpha x be 0, and you have some also let's say a renormalization condition that that asks that alpha of x will be constantly equal 1. And as you can imagine, then the web flow is the flow that is generated by this vector field. So in the previous example, the web vector field is just the dz, that is the vertical vector, and the flow will be just a vertical translation, let's say. And again, just to give you some example and to show that this kind of dynamics arise in a very large in a very large class of systems. We can think. We can construct what is called the HOPF flow. Actually, just consider R4 and put an Hamiltonian H on it. So just a smooth function defined on R4, taking real values. So the easiest one, it's 1 squared plus 6q squared plus y1 squared plus y2 squared. And you can consider, so you can look at the energy level associated to 1. So you will obtain just the free sphere. And since the Hamiltonian is autonomous, you know that every energy level will be invariant by the flow. And for example, here, when you consider your Hamiltonian flow restricted to the energy level corresponding to 1, you obtain actually what is called the HOPF flow. So our contact manifold will be just the free sphere and with this contact form. And in particular, it gives rise to what I found a very, very beautiful picture that is due to Patrick Massot. You have so the S3 that you can just think about it as L3 with a point at infinity that compactified everything. And there, every point actually belongs to a periodic orbit, and every orbit is they share the same period that are all of period 2 pi. So here there is a nice picture of what the dynamics looks like. Okay, so. I just wanted to give you some ideas of the richness also of the contact structure, and as we said, so we wanted to look at contact flow, but also the Axiom A flows. So in order to speak about Axiom A flows, I need to introduce, or I would say like to recall to all of you the notion of hyperbolicity. So let's consider a flow phi defined on our three-dimensional manifold M. Let's consider C1 flow. We say that a compact set lambda in M is a hyperbolic set for our flow if, of course, lambda is invariant for our dynamics, and moreover, we have, let's say, a very nice splitting of the tangent space in the following sense. For any point x in our lambda, the tangent space can be decomposed as a vector space that is so the space spanned by the flow vector field, what is called the stable subspace, that is so a vector subspace where we have a uniform contraction under the action of the differential in the future, and an unstable subspace where the uniform contraction arise, but when you look at the differential in the past. So just to give you an idea with a quick picture, let's consider a point. You have like your flow lines that corresponds to the must be thought as the direction, of course, generated by our flow vector field. And then let's say on the you can identify a plane. So in our case, since we are in lower dimensional dynamics, that is complementary to our flow vector field. When you have a stable direction that will be contracted in the future, and an unstable direction that on the other end will be contracting in the past. And so, for example, we think about NOs of systems where you have that you consider, for example, when you have that your hyperbolic set is actually the whole 3D manifold. But some, let's say, generalization, I would say, of NOs of system are actually Axiom A flows. And in order to introduce it, I want to say that we want that the superbolicity condition is realized, but in a smaller set, not on the whole manifold, in what is called the no-wandering set. And so we say that a point is a no-wandering set if you have your point, you can consider no matter which neighborhood of it, and no matter which time, big T, you will always find a time small t greater or equal than your starting big T, such that your neighbor revolves in some ways, but it let's try to, but it will still come back to the it will still meet the initial neighborhood. So there are points that somehow, let's say, come back to itself. And so the omega of our phi will be the set of all the non-wandering points. So as we were saying, we say that a flow is axiom A if the non-wandering set is hyperbolic, so in the sense that we just discussed. And moreover, we ask that periodic orbits have to be dense within the non-wandering set. In particular, this kind of flows present a very nice decomposition that goes back to Smale, so in the 60s, thanks to his spectral decomposition theorem, where actually proved that the non-wandering set can be decomposed into a finite collection of, let's say, isolated periodic orbits, and a finite collection of some lambda I, that is what are called basic sets. So let's think about the more like the more or less the stone that compose your no-wandering set, and which is, so these basic sets are sets where you have where the periodic orbits are dense, and moreover are transitive components, in the sense that within any lambda I there exists a point whose orbit will be dense in lambda I. And every lambda I actually is this decomposition is very interesting, because this allows you to describe every lambda I in terms of some symbolic dynamics, because the dynamics restricted to each lambda I is actually semi-conjugated to a subshift of finite type. So just to give you again an example. An example of axiom A flows could be the systems that arise in open dispersing billiards. So what I mean by this, so just consider the plane, and consider a finite collection of obstacles, O1 and 2 OM, at least 3, that are strictly convex domains. And what we do, and we ask that for any for any triplet of obstacles, we want that the third one does not belong to the convex envelope of the first two. So this is what is called billiards without eclipse. And in this framework, you can look at the billiard flow. So what we want to do, just think about just playing billiards, but instead of doing it inside a table, just switch the rules and playing it outside the tables. So you can you have your ball and you just fix a direction. You shoot your trajectory, and once you encounter your obstacles, you just reflect according to the reflection law. So with the same angle that determined by the trajectories and the normal. And again, you start again, and as soon as you meet an obstacle, you will bounce another time. So as you can imagine, of course, since I want to remain in R2, there will be, of course, trajectories that will escape to infinity. Just consider a ball here and shoot it in this direction. Then it won't encounter any obstacles, and so we are not able to, let's say, describe it. Its dynamics, it's very trivial, let's say. But we can restrict our attention to the trapped set. That is exactly the non-wandering set. That is, in other way, the set of all orbits that are not escaping to infinite. So the orbits that will remain there and bounce infinitely many times in the future and in the past. And this is exactly an example of an Axiom A flow when you consider your billiard flow, where the hyperbolicity comes from the strict convexity of the obstacles. So here you have just, I think it's a numerical simulation due to the Otal, so of what the trap set look like for no pairing dispersing billiards with free obstacles. Okay, perfect. So now that I have tried to tell you a little bit about the kind of system that you want to look at, let me just present you the result that we obtained with Martin, and then I will try to give you some ideas of the proof. Okay, so let's think about two Axiom A flows of class CK with K at least 2 on some 3D manifold. And we assume that they are also contact flow. So in particular, we want that each phi I preserves some contact form lambda I, in the sense that so the pullback of the alpha I must be equal to the alpha I. And then if there exists lambda 1 and lambda 2 that are respectively basic sets for phi 1 and phi 2, and you have an application C0 that goes from the first basic set to the second one, that is, I will be back in a minute to this strange, let's say, hypothesis, that is an iso-length-spectral orbit equivalence. Then we can show that the flow restricted to the corresponding basic sets are actually conjugated by an application that is more regular than what we expect. That is actually C1 beta with for some beta greater than 0. And moreover, also we have that the contact structure are preserved. It means that the contact structure of the first flow is sent through our conjugation to the contact structure of the second one. And so just before continuing, let me just precise so the main hypothesis that we are making. So what I mean by an orbit equivalence? So I mean just our C0 will be so an application from the first basic set to the second one, such that, so roughly speaking, it's an application that sends orbits to orbits, but for which we cannot control, let's say, the speed. So to formalize it, you have some function theta. That is the function that allows you to, is modifying the speed at which you go along the your orbit. And we want also that this orbit equivalence is iso-length-spectral, in the following sense, that if you consider any point on the first basic set that is a periodic, that belongs to a periodic orbit, we want that the length of the periodic orbit of this point with respect to the first flow must be equal to the length of for the second flow of the periodic orbit associated to the image of the point. Okay, so in the 10 minutes that that remains me, I would like to give you some ideas of the proof that is in some parts are reminiscent of the work of Otal for geodesic flows. So there are different steps that we can make. The first one is that thanks to the iso-length-spectral hypothesis, we can pass through this orbit equivalence C0 to some C that is actually a flow conjugacy by using Lifshitz theorem. The hypothesis of on the spectrum is telling us that somehow we can synchronize the flows, that not only we are sending orbits to orbit, but we do it by respecting the time. And once we have this, then we can build what we call the quadrilaterals that are present also in the work of Otal in the following sense. So let's consider just 4 points in our basic set, so lambda, and we want to build a quadrilateral by starting from the first point, going along the stable manifold for the flow of the first one and up to the second one, and then moving along the unstable manifold of the second point, and then again the stable manifold of the third point, and the unstable manifold of the last point, up to and we will stop when we will meet again the flow lines of the starting point. This quadrilateral actually will not close, because of let's say the non-integrability that is carried by the contact structure. But we can say so that the last point, of course, we can denote it as as the flow at some time h of q of the first point. And this h of q, so for us, we will play an important role, and it we call it the temporal displacement of our quadrilateral. And there is a way to try to calculate. The aim here will be like to try to calculate this temporal displacement, and a way to do it is using actually stable and unstable hoonomies. In particular, for Axiom A flows, there always exists a Markov family. So by a Markov family, I mean a finite collection of rectangles that enables you to, let's say, somehow to code your dynamics. It means that any orbit will meet infinitely many times in the future and in the past our finite family. And once we have fixed this finite collection of rectangles, we can just pass through. We can, let's say, reduce the problem in a lower dimensional setting, because we can look actually at the first return map that we denote by F on our collection of rectangles, and we will use also the tau that is actually the first return time. So here you have that if you have a point x here, this one will be f of x that corresponds also to our flow at time 2 of x Okay. So once we do this, actually, we have that through the stable holonomy can be expressed in terms of this first return time. So in the following sense, just fix a point x that belongs to one of our rectangles, and we can compare actually what happens. So we can try to look at the stable manifold for the flow and the stable manifold for the first return map. We move along the stable manifold for f up to a point y, and then the point z that is obtained by looking at the intersection of the flow line of y and the stable manifold of our flow will be actually of course the flow at time h of s of y, and this h of s is actually what we call the stable holonomy that could be described in terms of the return some infinite sum of the return first return time for y and for x. The fact is that this temporal displacement, so the starting, let me come back just to the initial quadrilateral. Here, so with the stable holonomy, we can actually we can describe so this contribution to the temporal displacement, and then you can do the same by looking at the unstable holonomy between x2 and x3, and also for the other point, and some of them will actually give you the temporal displacement of the starting quadrilateral. And so this allows us to express it in terms of this alternate sum of first return times of the extrema of our quadrilateral. The fact is that once we have this formula, this allows us to tell that the h of q is actually determined by the length of periodic orbits. So it's just a matter of it is fully determined by the let's say the spectral data in the following sense, because we can like consider the quotient with respect to the flow direction. And so in particular, our quadrilateral will close up in some q bar that you can obtain by projecting on a rectangle. And so without loss of generality, we can assume that two of the opposite extrema are actually fixed point for the first return map, say periodic. And the fact is that so the other extrema will be just we could interpret them just as of course heteroclinic intersection. And once we have this, we can always find by using so the tools that arise from symbolic dynamics. We can always find a periodic orbit that is like more or less tracing our quadrilateral, and so with a little bit of calculus, we can just express our h of q in terms of let's say this periodic orbit. And so why we want to look at this temporal displacement, because it has also on the other end a geometrical interpretation in the following sense that think about our quadrilateral and just projected it by doing the quotient for the flow lines on our rectangles. So we know that we have said that we obtain so a real quadrilateral that is closing up. And this h of q, just by using some standard Stokes theorem, our displacement is actually the area of this quadrilateral, of this, let's say, rectangle. So in particular, if we start by some phi1 and phi2 that share the same length data, since the temporal displacement is the same, it means also that the area of this quadrilateral must be the same. And according to this, then we can just look at the derivative along the stable and the unstable direction of our conjugation psi in the following sense. actually we can, with the help of the stable and unstable variation, so just consider a point x that belongs to our basic set. Consider then the unstable manifold for the first return map, and on it we identified 2 points y and z, and also we want to use also the stable manifold respectively of x, y, and z. And we can highlight some rectangles. So by using this construction and using the fact that we have a local product structure, so we will have the smaller rectangle and a greater one, and we can look at their image through our flow conjugacy C. And the fact is that now just think about, so I don't want to enter into some the calculus, but if you just imagine that this is straight rectangles, and so in order to calculate the area, you just use the base times the 8 of the rectangles. And so the fact is that if you consider the area of the bigger rectangle over the area of the smaller one, so for the first flows, you will see that let's say the 8 will be erased, and so we will end up with the distance between x and z over the distance between x and y. It is, let's say, more or less the ratio of the area of the rectangle. Since we know that the area of the rectangle are the same, this is exactly the area of the ratio of the area of the rectangles that are image of the starting one. And in the same way, we will obtain that this is more or less the distance of psi of x, psi of z over the distance between psi of x, psi of y. And in particular, it means that we can show that the incremental ratio when you of our psi, actually we can prove that it is a Cauchy sequence, and this allows us to say that so the derivative, at least along the unstable direction, exists, and we can do actually we can actually prove something more, that is also older. So for some beta, in Whitney sense, in the sense that we are just allowed to take the incremental ratio just of points that belong to our starting basic set. And in the similar way, you have that also the derivative along the stable direction of our psi is also exists, and is also older for some beta between 0 and 1. And then just to conclude, because I think that I'm running out of time. Once you have that the derivative along the stable direction, the unstable direction exists, then as I told you before, you can deduce that the psi actually is C1 just by the application of some Giornata lemma for this is in particular a version of Nicola and Rock of 2007 for hyperbolic basis sets in 2-dimensional. And so we have gained that the regularity actually of our flow conjugacy, and the preservation of the contact structure. It comes from the fact that we are constructing a DinAmica conjugacy. So in particular, the stable direction of the first one will be sent to the stable direction of the second one, and the same for the unstable direction. But the stable and the unstable direction are exactly the contact structure, the contact plane of our initial contact form, while the flow vector field is actually it's sent the first one is sent exactly to the second one, and so it allows us to say that it allows us to reconstruct, let's say, the contact form as and be sure that the first one is sent through a warp C exactly to the second one. And I think that I run a little bit out of time, so I thank you very much for your attention. So we just keep to the last one, and yeah, thank you very much. And
thank you very much, Anna. Actually, you were not over time. You started a little late and you ended exactly on time as far as I'm concerned. Perfect. So are there any questions? We have, once again, some time for questions. This is actually the second and last talk of the day. So we have, like say, more free time to ask questions, although we want to move on to the other activity for today.
Actually, I have a question since we have time. So what is the application to open dispersing billiard you were mentioning?
Yeah, thank you. So it was like the last slide. Thank you, Alfonso, for the answer, for the question. And the fact is that, so in the case of open dispersing billiard, you can, when you have like, you want to compare two dispersing billiard, actually, we have already observed that we have already mentioned that the billiard flow is an Axiom A flows because of the convexity, the strict convexity of the obstacles. But the fact is that not only this, it is also a contact flow. There is like I think that a very good reference for it is like the book of Chernow-Markarian. And so actually it represents exactly a kind of systems where we can apply the result, and in particular in the following sense, because so we want to apply the result. We want to have Axiom A contact flows on a 3D manifold. That has some iso-length-spectral orbit equivalence, and this is actually given more or less, I would say, like for free, if you ask that the two billiards that you look at share the same marked length spectrum. So in particular for the open dispersive billiards, there is a canonical way to code the dynamics, just put some label on, of course, sorry, think about two open dispersive billiards with the same number of obstacles, otherwise it could be complicated. And you can just obtain, so you can use some, you can obtain some symbolic dynamics, and so the two billiards could be actually topologically conjugate. That gives you, so let's say, the orbit equivalence part. And if you ask that they share some marked length spectrum, that is, so at every periodic coding, you associate the length of the periodic orbit with that given coding. If you ask that they share the marked length spectrum, that you could you obtain that the billiards are actually you can obtain more just using some thermodynamical formalism. They are actually CK-1 conjugate. So, and in particular, you send the contact form of the first one into the contact form of the other one.
Thank you. Yes.
Thank you.
Okay. Any more questions?
Just a small curiosity about this example. So, but this assumption about marked length spectrum, is it possible that, is it something that you can control, let's say, just by moving the obstacles?
You mean if you just...
Yeah, you just, for example, know that if you just move one obstacle by a given function which is regular, then you keep obtain the equivalence.
I think that, so you mean like, for example, just me, I will try to, you mean if you start, for example, let's say with two billiards that are exactly the same, but on the other one, the third obstacles, you move it like here,
Yeah, maybe just control the movement of the something like this.
I think
Maybe
that as soon as you move a little bit, you are changing the Martin Leguil spectrum, because just think about taking just periodic orbits of period 2. So it would be like here, that would be like orbits that bounce with a perpendicular direction. So something like this, that is going up. And if you move a little bit the obstacles, I think that you can, for example, just over. Okay, it's not so. There you can modify the length of this orbit. So I don't think that the Markov length spectrum is stable under small perturbation of the table.